No questions? All right, let's look at Module 5, better known as 1 Bravo. Identify basic facts about modulation techniques and transmissions mediums. Again, got to get 70% on the KPC. This one is 10 questions. So you got 1 alpha, which is 12. This is 10, and it is chock full of modulation techniques and transmission mediums. We're going to look at the AFSC. What are you going to deal with? You're going to deal with all types of ways to modulate the radio. You're going to look at ways to modulate modems that go out over the Wi-Fi or send to the distant end. There is a lot of different mediums out there, and how we are going to take the information that we generate and send it out over the airways. We're going to look at modulation techniques, better known as amplitude, frequency modulation, single sideband modulation, analog to digital conversion, which is the precursor of that, how we get this signal to you guys. We're going to look at types of modulation when it comes to digital information. We're going to look at transmission mediums. We're going to look at 2 different types. One is wired versus wireless, which is looking at guided and unguided media. So let's take a look at general information here of the two. Amplitude modulation is exactly what it means. We're modulating the amplitude of the carrier. It is the easiest to do, simplest to do. Doesn't take a whole lot of equipment to do it. You can see that we have the audio, which is the modulation. We tried that in our transmitter, and then generating a oscope variation of looking at that waveform. The upper part of that signal is normally the upper sideband. The lower part is the lower sideband. The middle part is the carrier carrying the audio. And then when it comes to amplitude demodulation, pretty much it's nothing more than a diode. Excuse me. You do have problems with it called fading and distortion. There are some advantages to it. It's pretty simple. Disadvantages is it's not very efficient. It also has high levels of noise. We look at applications of AM. Yes, they're still out there. We still have aircraft radio that still uses it, VHF side of the house. Single sideband when we're transmitting out that information, a technique of AM. And of course, something called QAM, Quadrature Amplitude Modulation, that is normally in the digital aspect of everything. When we look at broadcast transmissions, they're pretty low on the medium frequency band, and also air radio, which is the VHF side. We'll get to look at all of the information when we get to I think it's 2 Alpha, Bravo, and Charlie. Okay, single sideband and quadrature modulation are also a part of it. Single sideband has a relationship with HF, whereas quadrature is more for your computers. But it's getting to the point where even it's being used in the HF realm. Some of the ham radio operators are now using it to send digital information. Frequency modulation. We had amplitude, which modulates the amplitude. Now we're looking at the frequency. Normally it's a change in the frequency and how we modulate it. Back in the day, you got the audio instead of what looked to be like a variation in amplitude. Now it's all about the frequency. See in different aspects, let me show you here, that there has been a change in frequency here, change in frequency here, and a change in frequency here. That's what frequency modulation is all about. Normally in that 30 megahertz and above, when we're talking military. You also know FM on your radio dial in the car or in your dorm room when you want to pick up some listen to if you're not listening to Spotify or any of the others online. You can pick these radio stations up. I think it's 88 to 108. Again, that's what I use on both the transmitter and the receiver. Carrier frequency is normally in line with the audio signal. Big thing is you don't have a whole lot of interference. We do use wideband FM, which is in that 200K. That's the reason I always talk about the minimum of 200K separation. And you can look at the FM dial and look at that as far as 200K off. Now, when you start getting into more and more like SATCOM, it's 200 meg off. Again, you got narrowband, you got a varactor, which is a diode oscillator. You still using phase lock loop in some of these. You have a demodulator, the detector and discriminator that's being used in there to either modulate or demodulate. You have advantages, again, noise. Don't have the noise like you would with AM when you compare the two. It is more efficient with the FM as far as power. Problem is, you use a wider frequency spectrum as opposed to AM. AM, you don't need as much. FM, you do. You do need more complicated equipment with it. And sometimes when you don't have a good filter on it, you do have what we call sidebands or major harmonics, which can cause problems later on down the line. We look at single sideband. This is a form of AM. The difference is you're only using one side of it. That's the gist of it. Single sideband. Remember we talked about an upper and lower sidebands. We're only using that. We're eliminating the carrier. Okay, so that's what it is you go from, let's say, normally on an AM voice radio that we've had out there, could be 2.7K on each side of, for a grand total of 6K hertz in frequency spectrum usage. Whereas now with single sideband, we're down to 2.7K on one side. So the carrier has been eliminated and the other sideband has been filtered out. That's the nice thing about HF. It uses frequency spectrum conservation. You can see how we can use it now with CW modes versus single sideband versus AM versus FM. You can see the comparison that single sideband can be used well. Definitely conserves the frequency spectrum. This gives you an idea of the comparison with the AM signal versus single sideband. Again, the FM is much larger than the AM signal, and then one of the sidebands is definitely smaller than the AM. That's how we can compare them. You can transmit further with single sideband. Normally it is in the HF realm, is where we like to use it, but it can be used in others. It depends on its use. We talk about the peak envelope power, lower sideband, upper sideband, and what we call a double or dual sideband. That is basically two sidebands in the lower and two sidebands in the upper. Depends on how you're wanting to do it. Or you can have just the single sidebands itself. One on the upper, one on the lower. We had a radio, trying to think of the name of it, but it used to be in those old TOAM vans that go to ACS squadrons, and they could do what's called double sidebands. In other words, two of each sidebands. Pretty wicked on how they're able to do that. We have some things like variants called independent sidebands. You're going to see this next one pop up, which is amplitude modulated equivalent, which is the upper sideband and the carrier together. That way you can use not only UHF to be able to listen to it. It shouldn't be, or not UHF, but actually any type of AM radio will be able to listen in when you broadcast, even though you've eliminated the lower sideband. Here's some advantages. 1/4 of the power when you compare it to AM. It does have reduction in spectrum. Definitely improves the signal noise to noise ratio because you've eliminated one of the sidebands in the carrier. We're going to look at something called analog to digital conversion. This is called pulse code modulation, PCM. It was developed by Dr. Nyquist. There was also another guy with him, but he gets most of the credit. And what he said is you always want to sample your analog voice twice the highest voice frequency. Normally he came up with the standard of 4,000 hertz, which, with you and I talking amongst each other, most of us won't even get close to 4K. But he just gave it a nice round figure just in case we had other people that could go higher and, of course, lower and things like that. So it basically ends up a 8,000 times a second that's being sampled. We'll get to that in just a minute. But Nyquist theorem is twice the highest audio frequency. But I'm going to ask you guys, anybody use the free software program called Audacity?
Yeah, once in college.
Audacity is a pretty good program for being, freeware. I've used it many a times. The more you sample, the better the quality. But in our case with radios, you only need to sample 8,000 times a second. That's 2 times 4K. And you're only dealing with your voice. You're not dealing with music or anything like that. As compared to Audacity, which the last time I looked a couple months ago was up to 320K of sampling. That's a lot. Why? Because you want to get it as close as you can to the original signal. The more you sample, the better off you are. But it also takes processing speed. That's another reason why he capped it off at 8K. There are 3 steps to PCM: sample, quantizing, and encoding. Sampling is taking that audio signal and sampling it 8,000 times a second. That came from the Nyquist theorem. The next one is quantizing. So we're going to take all of those pulses that we got and apply it to a diagram or a chart, and we're going to assign it a number on that chart based on where those samples hit. Then we're going to take it, and there are 2 different types of this when you apply it to these diagrams. One's called uniform, the other one's called non-uniform. Uniform is because all of the steps are equal, versus non-uniform, most of the steps have been brought closer to the center, but there's still the same amount of space in there. And there's a reason why I would go into great detail, but we don't have the time for that. What it does with non-uniform is it gives it a better replica of the numbers, and with uniform quantizing, you end up with something called quantization errors. You'll read about it, hopefully, in the study guide workbook. Now we go to the next step, which is encoding. So we've sampled it, we put it on a diagram, which is quantizing, and now we're going to give it an 8-bit number. That we call that a word. And then we're going to ship it out to give us, what does it sound like in that 1 second. That's what PCM does. Takes your analog voice, converts it to digital using those 3 steps, and there's many different variations of pulse code modulation that's out there. What I'm doing right now on Discord, when it gets to you, you're going from analog, which is going into the mic here. When it gets to you, it's gone from analog to digital, being modulated, sent out to your end. Then it gets demodulated digitally, and then turns it back into audio so you can hear it. And of course, the 8-bit word, first 7 bits are the actual numbers that you just put in there, and then you end up with the last bit being whether it's a positive or negative in that word. We have frequency shift keying. Oh boy. Now we're getting into a little bit more background before radios truly became frequency shift keying and amplitude shift keying started coming into play, especially when you're looking at frequency shift keying because of the old teletype. You're looking at, remember, trying to think of the doggone name, the Titanic, when it went down, the SOS, that was all done through your that type deal. That's basically a combination, or actually a frequency shift keying, because you're given a specific tone. In this case, ones and zeros. Ones versus zeros in frequency. So one frequency would be a 1. The 0 would be a different frequency. It doesn't change until you go to a different digit. In other words, a 1 or a 0. You can see down here, when we're looking at this, this is a 1. You can see it's one different frequency. It changes when we see a 0. There's a 0. Then we have a 1. This is where the frequency changes, but it doesn't change all through the ones each time that there is a 1 until you see another change in the logic. There's a 0, so it's going to change right there. Amplitude shifting, the differences between amplitude versus frequency, you can see it right here. Ones are one amplitude, zeros are another amplitude. An easy way to do this is 0 is probably going to be a lower amplitude and ones are a bigger amplitude. That's shift between ones and zeros when it comes to digital. Binary phase shift keying is kind of crazy. Wrong arrow, but see, we have a logic of 1. Go all the way over here. Okay. How the time flows. You have a logic of 1 here. You can see that we go down, and then we are going to shift the phase of the analog signal. In our case, we're going to shift it 180 degrees here. We're shifting it at the 0 degrees here. You can see the differences between the ones and the zeros when we're doing this. All you have to need to know is with binary, I'm shifting it. It's when we get into quadrature that instead of shifting at either here, here, or here, at that 0, 180, whatever you want to call it, we're shifting it at different places. This is a, could be a 0. Look at this one. Look at where it's shifting here. So you got a small shift here. You have a large shift here. So in other words, when you're looking at 0, 90, 180 degrees, and 270. Now, what does it mean by 2 logic bits? Everybody else was either a 1 or a 0. Because you're using this, you actually have 2 bits of information and not 1. What does it mean? It means that depending on where this shifts, it could either be a 0, 0, a 0, 1, a 1, 0, or a 1, 1. Those are 2 logic states that gives you 4 different areas of where it needs to, or gives you 4 different bits of information. And then we get the quadrature. Oh my goodness. Quadrature actually has a couple of carriers on there, and they do the same thing as quadrature phase shifting, except now instead of having 2 bits of information, they have 4 bits of information. They can start at 3 bits because one can only, let's just say one carrier shifts twice at the 0 or 180. The other one will shift in 4 different places, which gives it 2 bits of information. So that's how it can go from 3, and if you go to 4, you can actually have 2 carriers that do the same thing, only they're in different areas. In other words, you can see that we have 2 carriers here, and we can identify it. Now with quadrature, you can go up into the 264 to 512. There's probably even further along the line as far as technology is concerned. Your newer TVs do this, by the way. HF is starting to do it, and the Air Force is going to that particular area. When we look at transmission medians are changing here, we're going to go wired versus wireless. It's pretty easy to understand. Wired is you're connecting it to physically something along those lines of like a Cat5 cable or a phone cable or whatever you need to do. And then you got wireless, which is over the airways. There are a number of ways to identify it. This is the easiest one that I can come up with. You have guided and unguided is the way to do it. Unguided would be wireless, guided would be wired. We have 3 of each on there just to give you an overview. Let's take a look at each one of them. Guided, you have high speed, secure, used for short distances versus unguided, which is more likely for over the air. Now with this you can look at twisted pair, coax, fiber optic, the unshielded pair. There's some advantages and disadvantages to it, but the whole idea is you have a physical connection. You have the shielded twisted pairs, another one. There's some advantages and disadvantages. The nice thing about that one is it has a shield to block all the crosstalk and things like that might get over on the other cables. Coax cable has 2 conductors. It's got a center pin or the center conductor and the outer section, which is a shield. Normally you have baseband or broadband with it. There are some advantages and disadvantages. The big disadvantages is you got a single cable failure. You're not going to get your whatever it is that you need to get over, like your internet, things like that. So if somebody cuts the line, you got to wait. Somebody repairs it. Fiber optic, this one can really handle a lot of data that's on it. That's the big thing. And it does have advantages and disadvantages. The big one is cost. When we go to unguided, this is about over the airways. There's 3 different types: radio waves, microwaves, infrared. Normally from 3K to 10 gig, terrestrial, satellite. Anything beyond the, I'm trying to think of that last one, is EHF. Then you start getting into the light, which is also RF, and after that you get into the X-rays. So microwaves normally line of sight. You have to line the antennas with each other, 1 gig to 300 gig. Infrared, very short distance. That's some of your remotes. And then you have the other one: microwaves, radio waves, microwaves, and infrared. Okay. Infrared is on that verge of light, by the way. That's a very short wavelength. All right, so we went over modulation techniques, covered just brief explanations on these to include the PCM and things like that. Then we looked at transmission mediums, wired versus wireless, and guided and unguided examples. Now, any questions? A lot of information to be going through, and it's going to be fun for the exercise.